This is a video walkthrough for practice 9.1. In number 1, to solve this equation, we can put it in exponential form. Base is 3, exponent is 2 because a logarithm equals an exponent. So 3 squared is equal to 4x plus 8. Subtracting 8 from both sides, we get 4x is equal to 1. So x must be equal to 1/4. In number 2, if the natural log of a equals natural log of b, then a is equal to b. We can undo the logs if we just have a single log on each side. And then subtracting 2x and adding 3, we get 3x is equal to 4 and x is equal to 4/3. When we solve this type of equation where you have two different natural logs, each with variable arguments, it's necessary to check that solution. So before we confirm here, let's check that solution. And the natural log of 2 times 4/3 plus 1 should equal the natural log of 5 times 4/3 minus 3. Okay, we have 8/3 plus 1, which is 3/3, gives us natural log of 11/3 on the left side of the equation. And then 5 times 4/3 is 20/3, and minus 3, that's 9/3, gives us natural log of 11/3 on the right side. Since we're taking the natural log of a positive number, this is a valid solution. All right, in 3, we have an exponential equation, so we can re-express both sides as powers of 6. 6 to the 0 power is 1. Now just equate the exponents, so 5x minus 2 is equal to 0, and x must be equal to 2/5. In 4, we can re-express both sides as powers of the same base. 25 is 5 squared, and we're going to raise that to the 3x minus 2 power. And when we raise a power to a power, we multiply the exponents, so 2 times 3x minus 2 is 6x minus 4. Now we can just equate the exponents since the bases are the same, and subtracting x and adding 4 to both sides, that's going to give us an x value of 2. Since it's an exponential equation, we don't need to worry about domain. All right, in number 5, we have what looks like a change of base, so we can just change the base back to log base 2 of 7x minus 6 is equal to 3. And so in exponential form, that's 2 to the 3rd power is equal to 7 minus 6. 8 plus 6 is 14, so 7x is equal to 14, and x must be 2. Not necessary to check this one since we only have one log with a variable argument in it. All right, in 6, we have a logarithmic equation. We can rewrite in exponential form. 3 to the negative 2 is equal to 2x minus 1 divided by 5. 3 to the negative 2 is 1/9. And to solve this equation, you can do one of two things. Multiply by the LCD, which is 45, or cross multiply. Both give you the exact same result. 9 times 2x minus 1 is equal to 5 times 1. Distributing the multiplication over the subtraction, and then adding 9, we get x is equal to 14/18, which reduces to 7/9. In 7, we have an exponential equation for which the bases can be expressed using the same base 2. So 2 squared to the 2x plus 1 is equal to 2 cubed raised to the x minus 2 power. Power to a power, we multiply the exponents and then equate the exponents. Subtracting 3x from both sides and then subtracting 2, we get x is equal to negative 8. In number 8, if we have two logs that are equal to each other, that means their arguments must be equal to each other. And so 3 minus 2x will be equal to x minus 12. Adding 2x to both sides and then adding 12, we get 3x is equal to 15, so x must be equal to 5. We need to check our solutions when we have two variable quantities that are arguments of logarithms. So let's do a check on this one. If we check, we get log of 3 minus 2 times 5 equal to log of 5 minus 12, and that would give us log of negative 7 equals log of negative 7. Each of these expressions here is not defined, so that means that this is an extraneous solution, and so in fact there is no solution. When you're asked to solve an equation, the appropriate answer is no solution if there is no solution to the equation, rather than undefined. Undefined is used to describe an expression. No solution is used to describe the existence of a solution. In number 9, I'm going to divide both sides by the natural log of 7, and that we can cancel that factor there. And then we have what looks like the change of base formula on the left side. So the base, when written in its original form, would be 7. Log base 7 of x minus 2 is equal to 2. Written in exponential form, that's 7 squared is equal to x minus 2. Since 7 squared is 49, adding 2, x is 51. In number 10, if log of a equals log of b, then a equals b, so we can just equate the arguments of the logarithms and then move everything to one side. So I'm going to add x and subtract 5, and we can factor to solve. X minus 3 times x minus 7 is equal to 0, which means that x minus 3 equals 0 or x minus 7 is equal to 0, and so that's going to give us two solutions, 3 and 7. And we need to check those solutions very carefully. Assuming we've done everything correct, we just need to check to see if we, in fact, get the log of a negative number when we plug in. When we plug in x equals 3, we get log of 5 minus 3, which is log of 2. Valid. That's the log of a positive number. When we plug in 7, we get log of 5 minus 7, which is log of negative 2. Invalid. So that is an extraneous solution. So x equals 3 is the only valid solution for this equation. In number 11, we can re-express each of these with common bases, base 3. So 3 to the x plus 5 times 3 to the third raised to the 2x minus 1 is equal to 3 to the second power raised to the x plus 6. Power to a power, we multiply those exponents, so that's 6x minus 1 and 2x plus 12. When we multiply like bases together, we add their exponents, so that gives us 7x plus 4, and on the right our exponent is still 2x plus 12. Now that we have 3 to the a equals 3 to the b, that means that a and b, the exponents, must be equal to one another. Subtracting 2x and subtracting 4, we get 5x is equal to 8, so x is equal to 8/5. And of course, now looking back at my solution, it wouldn't be right if I didn't make a few mistakes. I'm going to go back and correct. When we raised a power to a power here, 3 times 2x minus 1 is 6x minus 3. That means that when we add the next exponents, that's going to give us a plus 2. And so we're going to change that to plus 2. And so now when we subtract 2 from both sides, we're going to get 5x is equal to 10. And that's going to give us a solution of x equals 2. In number 12, this is a logarithmic equation which we can write in exponential form. 2 to the third power is equal to x squared minus 2x. I'm going to subtract that 8 from both sides of the equation and then solve by factoring. X minus 4 times x plus 2. So that means that x minus 4 must equal 0 or x plus 2 must equal 0. That's going to give us x equals 4 or x equals negative 2. If you have a single logarithm with a variable argument in the equation, it's not necessary to check. It's still going to give us a correct answer. In number 13, if log of a equals log of b and they're the same base, then 2x minus 5 must equal 7. adding 7 and dividing by 2, x is equal to 6. There's only a single variable logarithm in this equation, so it's not going to be necessary to check, but you certainly can. In number 14, we have an exponential equation here. So if we realize that 125 is 5 to the third power, then when we divide, we subtract exponents. That's 5 to the x squared minus 3 is equal to, and 1 over 5 to the 2x is 5 to the negative 2x. So now we can just equate our exponents. X squared minus 3 is equal to negative 2x. Adding 2x to both sides and factoring. If we set each factor equal to 0, we're going to get x is equal to negative 3 or x is equal to positive 1. In 15, when dividing, we subtract exponents if the bases are the same. So 4 to the x squared minus 3x is equal to, and 1/16 is the same as 4 to the negative 2. Equating exponents, x squared minus 3x is equal to negative 2, and we can add the 2 to both sides and factor. X minus 2 times x minus 1 is equal to 0. If we equate each factor to 0, x is equal to 2 or x is equal to 1 are our two solutions. In number 16, we have what looks like a change of base. So I'm going to rewrite this. Log base x of 6x minus 5 is equal to 2. Now we're going to rewrite in exponential form. The base is x, the exponent is 2, and that's equal to 6x minus 5. That gives us a quadratic equation. We can subtract 6x and add 5 to both sides of the equation, and then factor x minus 3 times x minus 2 is equal to 0. That's going to give us two solutions, x equals 3 or x equals 2. Now we can check both of those solutions and see if they do give us logs of positive numbers. So if I replace x with 3, the argument of the log in the numerator in the original equation is 18 minus 5 or 13, and the log in the bottom is log of 3. Something about my solution is not making sense. And I suspect I have factored wrong here, so I'm going to go back and change this. X squared minus 6x plus 5 does not factor into x minus 3 times x minus 2. It factors into x minus 1 times x minus 5. So that's going to give us solutions of x equals 1 or x equals 5. Now we can go back and we can check each of these solutions. So checking here, we get for x equals 1, we're going to get the log of, what do we have, 6 times 1 minus 5, that's the log of 1, divided by the log of 1 is equal to 2. Something about that doesn't make sense. Now the reason why this one is an extraneous solution is not because we get the log of a negative number, but rather because the log of 1 equals 0. Okay, so we've just divided by 0. So we have an error there, a divide by 0 error. That's a little tricky to look for that extraneous solution. Let's check our other solution of x equals 5. And if we check x equals 5, we're going to get 6 times 5 minus 5 upstairs. That's going to be 30 minus 5 or 25. Log of 25 divided by log of 5 is equal to 2. And that one checks because change of base would say that the left side is actually log base 5 of 25, and that does equal to check. So we only have one valid solution. That's a little tricky extraneous solution there.